Now, let's look at the title here. Finding the limit of an indeterminate form of the type 0 times infinity, or infinity minus infinity, or 0 to the 0, 1 to the infinity, or infinity to the 0. These are indeterminate forms. For example, if I get 0 times infinity, I can't say that is 0 because infinity is not a number, it's a concept. It's telling you how the graph is growing. So 0 times infinity is completely indeterminate. So how do we find a limit? How do we evaluate a limit? Is it possible for the limit to exist? And the answer to that is yes. Even though we may get some sort of behavior that tends to 0 times infinity, that limit may actually end up existing. It may actually be a real number. So how do we tackle something like this? The first thing that we're going to do right now is see what happens to this product as x approaches 0 from the right. Let's just quickly check. As x approaches 0 from the right, x is approaching 0. And the natural logarithm is approaching negative infinity. So I notice that I have over here this indeterminate form right here. Nothing can be concluded about the limit at the moment because 0 times negative infinity, it just doesn't exist, doesn't make any sense. Infinity is not a number. So then that means that I need to try to do something else here, something. Let's try to be creative. So one way of being creative is to rewrite this expression as the natural logarithm divided by 1 over x. I am hoping that you're noticing how this expression is identical to the original one that we were given. What is really nice about this is that if we try to investigate the limit again, as x approaches 0 from the right, the numerator is nicely approaching negative infinity. And the denominator is now approaching, as x approaches 0, 1 over x is approaching positive infinity. So now notice how we have negative infinity over infinity. That's the classic form of indeterminacy that allows us to use L'Hopital's rule. So see, when we started, we just got 0 times negative infinity. This is not the indeterminate form that we need for L'Hopital's. This just said that we couldn't conclude anything about the limit. But then we got creative and we rewrote the expression as natural logarithm over 1 over x. And we checked the behavior of the limit. The numerator tends to negative infinity. The denominator tends to positive infinity. So the entire quotient tends to negative infinity over infinity. And there it is. This is one of the indeterminate forms that allows us to use L'Hopital's. So then I'm just going to make a note of the indeterminate statement. I am going to note that the limit as x approaches 0 from the right of the natural logarithm is equal to negative infinity, and the limit as x approaches 0 from the right of 1 over x is equal to positive infinity. So then I think that I'm ready to apply L'Hopital's rule. I'm just going to go ahead to make my differentiation easier. I am going to rewrite the denominator as x to the negative 1, right? 1 over x is x to the negative 1. And now in this step, I will differentiate. The derivative of the natural logarithm is 1 over x. The derivative of the bottom will be negative x to the negative 2. So then this is going to give us the limit as x approaches 0 from the right of 1 over x divided by negative 1 over x squared. Continuing right here, this will be equal to the limit as x approaches 0 from the right of negative 1 over x times x squared. which is going to be, I'm going to put the negative in front of the limit notation. So the limit as x goes to 0 from the right of just simply x. And that limit is going to be equal to 0. And see, at first it was unclear that this limit existed. We showed that yes, it exists and is equal to 0. How lovely. Here we have another limit. This is a limit as x approaches 0 from the right. If I just quickly try to evaluate the limit of each term separately, the limit as x goes to 0 from the right of 1 over x will be infinity. And then the limit as x goes to 0 from the right of 1 over sine x is going to be infinity as well. And that's infinity because as x goes to 0 from the right, sine goes to 0. So sine, the denominator is approaching something very, very small. So 1 over something very, very small is this, something very, very large. So then notice how this approaches infinity minus infinity. Well, again, infinity minus infinity, we can't say that is 0. We cannot, because infinity is not a number, so we cannot subtract infinity. So my limit is inconclusive. I don't know what to do here. That means that I'm going to have to try to do a little bit of algebra, try to get another expression that perhaps can allow me to evaluate the limit in a different way, hopefully even using L'Hopital's rule. So one way to do that, because remember that infinity minus infinity is not the indeterminate form that I need for L'Hopital's. This is an indeterminate form, but it's not the one that I need. For L'Hopital's, I need 0 over 0, or I need infinity over infinity, plus or minus that. If I get infinity minus infinity, that is an indeterminate form, but it's not one of these that allows me to use L'Hopital's. I need to get one of these indeterminate forms. So the way to achieve that is to rework this expression. Try to rework it out, maybe by getting a common denominator, getting a new expression, and hopefully analyzing the limit again and see if we get one of these indeterminate forms. So reworking the expression, this will be equal to the limit as x approaches 0 from the right. I'm going to get a common denominator, so I'm going to have x times the sine of x. In the numerator here, I am going to have sine x minus, and then x. So now I'm going to try checking the limit one more time. So let's see, as x approaches 0 from the right, the numerator approaches 0. Minus, again, this approaches 0. So then 0 minus 0 is 0. All right. The denominator, x approaches 0 and sine approaches 0. So then the denominator also goes to 0. And now I do get the indeterminate form of 0 over 0. So this now allows me to use L'Hopital's rule. I'm just going to make a note here, the same note as before, that the limit as x approaches 0 from the right of the sine of x minus x is going to be equal to 0. And the limit as x approaches 0 from the right of x times sine x is also equal to 0. So then, applying L'Hopital's, that will be equal to the limit as x approaches 0 from the right. The derivative of sine is cosine minus 1 divided by, but now in the denominator here, because I have a product, I'm going to have to use the product rule to differentiate. Not a problem. Using the product rule, the derivative of x is 1. So we're going to have sine x plus x times the derivative of sine, which is cosine of x. So this is, oops, no, that's not right. Cosine has an s, so cosine of x. So that's what we get. Then let me now check what happens if I try to substitute 0 from the right. What happens to the top, to the limit of the top? As x approaches 0 from the right, cosine approaches, cosine of 0 approaches 1. So this is approaching 1 minus 1. That means the numerator is approaching 0. Now let's look at the denominator. As x approaches 0 from the right, sine is approaching 0. Then x approaches 0, cosine approaches 1. So I get 0. Again, I have the indeterminate form of 0 over 0, which is kind of telling us that we're going to have to apply L'Hopital's rule once again. Notice how, just quickly checking the conditions here, the numerator is differentiable to the right of 0, in a small neighborhood to the right of 0, and the denominator is also differentiable, and it is non-zero. So the derivative of the bottom, the derivative of the denominator is non-zero, around 0. Now this is not obvious in this case. I am aware of that. What you will have to do is differentiate the bottom. I'm going to actually be doing that, and then you're going to see that indeed the denominator is not 0 in a neighborhood to the right of 0. So I'm going to use L'Hopital's. I'm going to make another note over here that the limit as x approaches 0 from the right of cosine of x minus 1 is going to be equal to 1 minus 1, which is 0. And similarly, the limit as x approaches 0 from the right of the denominator sine of x plus x times the cosine of x is going to be equal to 0 plus 0 times 1, which is 0. So then that allows me now to continue with L'Hopital's. So this will be equal to the limit as x approaches 0 from the right. The derivative of the top will be negative sine x. The derivative of negative 1 is 0, divided by the derivative of sine, which is cosine of x. And if you notice right here, I'm going to have to use product rule. The derivative of x is 1 times the cosine of x plus, then we're going to have x times negative sine x. So then rewriting this, we're going to have the limit as x approaches 0 from the right of negative sine x, all this divided by cosine of x. Actually, I'm going to say 2 cosine of x, because if you notice right here, I have cosine plus cosine. And then that's going to be minus x times the sine of x. So now I can try taking the limit one more time. And when I do that, as x approaches 0, the numerator tends to 0. The denominator, let's see, this part tends to 0, but this part doesn't. So this is what I have. I don't get another indeterminate form. I am going to get 0 on top divided by 2 minus 0, which is just going to be 0. So then the limit exists and is equal to 0. As the last example right here, they're asking us to evaluate the limit as x approaches 0 from the right of 1 plus x to the 1 over x. If I quickly examine this limit as x approaches 0 from the right, 1 approaches just 1 plus 0, and then 1 over x. As x approaches 0 from the right, 1 over x approaches infinity. So this is like having 1 to the infinity. And we know very well that 1 to the infinity is an indeterminate form. However, this is not the indeterminate form that allows us to use L'Hopital's rule to evaluate a limit. I need to get 0 over 0 or infinity over infinity to be able to use L'Hopital's rule. So then in this case, what do? what we're going to have to do is something very similar to before. We're going to have to play around a little bit with this expression so that we end up getting one of these indeterminate forms. So the way that we're going to do that is as follows. I'm going to take this expression right here, and I'm going to say, let y equals to 1 plus x to the 1 over x. Now, because in the base, I have x, and in the exponent, I have x, this is one of these kind of crazy functions that are a little bit strange. If you remember in the last chapter, the way that we dealt with this function was by taking the natural logarithm of both sides. So we're going to take the natural logarithm of y equals to 1 over x times the natural logarithm of 1 plus x. I don't have to put absolute values around y and 1 plus x because I am only dealing with positive values of x. So these are positive quantities. So what we really have here is the following. I have that the natural logarithm of y is equal to the natural log of 1 plus x divided by x. And what we are going to do right now is to consider the limit as x approaches 0 from the right of the natural logarithm of y. We are going to evaluate the limit as x goes to 0 from the right of the natural logarithm of 1 plus x divided by x. So we're moving a little bit away from y right now, and we are looking at the natural logarithm of y instead. But we're going to transition backwards a little bit later on. So really quickly right now, let's take a look. As x approaches 0 from the right, the numerator is approaching the natural logarithm of 1, which is 0. And the denominator is approaching 0 as well. So this is kind of telling me that we are approaching 0 over 0. This is the indeterminate form that allows us to use L'Hopital's rule. Look at this. The function on top is differentiable pretty much for all x values that are bigger than 0. And the function below over here is also differentiable. And when I consider the derivative of the denominator is non-zero because it's just going to be equal to 1. So then I am going to go ahead and make the note here, just as before, that the limit as x approaches 0 from the right of the natural logarithm of 1 plus x is going to be equal to the natural logarithm of 1, which is 0. And similarly, the limit as x approaches 0 from the right of x is going to be equal to 0. So now this allows me to use L'Hopital's. So this will be equal to the limit as x approaches 0 from the right. The derivative of the top is going to be equal to 1 over 1 plus x times the derivative of 1 using chain rule, which is just the same expression, divided by the derivative of x, which is equal to 1. So this will be equal to the limit as x approaches 0 from the right of 1 over 1 plus x, which is going to give me 1 over 1, which is just equal to 1. So now look at this over here. We now concluded that the limit as x approaches 0 from the right of the natural logarithm of y is equal to 1. It is clear here that I don't want to find the limit as x goes to 0 of the natural logarithm of y. I want the limit of just y. That's what I want. So, however, there is a way for us to get that. I want you to remember that indeed, y can be re-expressed as e to the natural log of y. And again, y is representing 1 plus x to the 1 over x. But the key here is that I can rewrite y as e to the natural log of y. So then I can continue my analysis like this. I am going to have now that the limit as x approaches 0 from the right of y, my expression, is equal to the limit as x approaches 0 from the right of e to the natural logarithm of y. Now, the variable has switched to the exponent, so the limit will switch up there as well. So this is equal to e to the limit as x approaches 0 from the right of the natural logarithm of y. And now remember, we already know that this limit, the limit as x goes to 0 of the natural log, is equal to 1. This is exactly the same limit there. So I can write this as e to the 1, which is e. As I noted before, we said that the actual number that would be the value of the limit would be a pretty significant number. And hopefully you can now agree with me. E is pretty significant. So we conclude now, therefore, the limit as x approaches 0 from the right of 1 plus x to the 1 over x, this was the y of before, is going to be equal to e. In fact, this is exactly the definition of e. E is equal to the limit as x goes to positive infinity of 1 plus x to the 1 over x.